Welcome to this week's CDAR seminar. My pleasure to introduce Baeho, who has been a visiting scholar at Berkeley now. This year has been just great to have him. He's in real life a professor of finance and business analytics at Korea University Business School, talking about conditional tail sampling for general mark point processes. Baeho.
Okay, thank you very much. Thank you for having me here, and thank you for coming and joining. In this talk, what I'm going to talk about is an efficient simulation method for general point processes, which we call conditional tail sampling, for investigating the tail, the distribution behavior of some random quantities under the tail event circumstances. And this is a joint work with Alex Gonley, who's at UC Santa Barbara. So motivation, my talk for today is going to be primarily about the problems of event counting within a given time horizon. Maybe simply counting the number of events sounds like a simple task, but actually they naturally arise in a wide range of disciplines in our daily lives. Examples may include counting the number of new patients in a pandemic season, or number of new insurance claims from the insurance company's perspective, or the number of corporate defaults during a crisis period, and perhaps observing number of the goals within 9 minutes of soccer game is quite prevailing and pervasive in our daily lives. But as I highlighted at the beginning, our focus is going to be the rare events, which often refers to the infrequent observable events with very small likelihood to be realized, right? But at the same time, I think it's fair to say that it can be systemically important events because it usually have quite widespread impacts, potentially leading to some instability of the entire system, simply because rare events will typically involve some extreme losses that may fall far from the unconditional mean. So this is why an accurate estimation of the distribution of tail behavior is both challenging but critical, because it can generate a serious problem, a crucial problem, if under the condition of the inaccurate estimates, okay, which can lead to suboptimal resource allocation or the missed opportunities during the crucial time period. So it's important problem. So here are our basically two questions to be addressed by this talk. The first question to be addressed is, what would be the likelihood that a given potentially larger number of events is observed by some relatively short horizon? Okay. If the probability can be quite small and tiny, it can be very important to address the second question, which is more practically important, I believe. The second question is, what would be the expected consequence under such a tail event circumstances? Okay. So to address those two questions, we basically consider a counting process n, in the sense that n sub p counts the number of events between time zero and capital P. And our focus is the tail probability, which is represented by this epsilon, to highlight that this epsilon can be very small. And this epsilon basically implies the probability of observing more than k events within the time horizon of capital P. Okay. So we have basically two parameters to control the rare event regime. One is k, which can be very large, and the other one is t, which can be relatively short. Okay. For the purpose of many real-world problems, the mathematical model typically becomes quite complicated, and sometimes it's very complicated to be solved by some analytical method or the numerical methods. In such a case, in most cases, the Monte Carlo method is the standard and useful method, and sometimes the only way for assigning some numerical value to the epsilon. There are pros and cons, but I'm going to focus on the pros first. Okay. So it's
simulation, right?
Monte Carlo simulation.
Yeah.
Right, exactly. So it's known that the convergence rate is independent of the dimension of the problem. So it's definitely an advantage. And another advantage that I'm going to highlight here is that the Monte Carlo simulation method can have some advantage in the sense that it can often generalize to more practically important and related problems for estimating this conditional expectation, right? So conditional expectation given the tail events, which can rarely observe. Actually, the estimation of this conditional expectation is not an easy task, because by definition, it's very difficult to observe such an event realized, right? So the problem is usually the distributional behavior of this random quantity X becomes totally different under the rare event circumstances. However, if we take advantage of the base formula, the left-hand side can be expressed as the ratio between two unconditional expectations where the denominator is just the probability that I mentioned before, okay? And also, just like the epsilon in denominator, the numerator can be also estimated by the Monte Carlo sample, because when it comes to the numerator there, we don't need the knowledge of the law of X conditional on the tail events. So it becomes a much easier problem to be tackled, right? So that's another advantage of using the Monte Carlo simulation method. But of course, we need to be careful when we try to implement the Monte Carlo sampling algorithm, especially for the rare events, because it can be very inefficient. Maybe you already know the problem, but in terms of the Monte Carlo, plain Monte Carlo, what I mean by plain Monte Carlo is the following. So if you take a look at this probability to be estimated, it can be also expressed as an expectation of the binary indicator variable specific to this tail event. So what I mean by this expectation in terms of the Monte Carlo simulation is just taking the sample average of the whole bunch of the zeros and ones, right? So if this epsilon becomes quite small, in most of the cases under the plain Monte Carlo scheme, this indicator value will be realized as 0, and just sometimes it's going to be 1. So on average, the plain Monte Carlo scheme requires approximately 1 over epsilon replications to get a single occurrence. So the further we move into the tail, the smaller epsilon becomes. We need more samples to consistently estimate this epsilon. So
just to say it back, so I'm sure I'm following. So the problem is that if you're trying to get a very rare event, you need a huge amount of data to get any population out there. Usually you don't have it.
By definition, it's a rare event.
Yeah.
Our focus is rare events. So definitely it's not going to work when the epsilon is too small to observe the sufficient number of events that hits the rare event threshold. That's the problem, primary problem of the plain Monte Carlo. So in general, to quantify the efficiency or the inefficiency of the certain Monte Carlo scheme, we take the definition of the relative error. Okay, to define that, we need to introduce something called phi to denote the unbiased estimate of the epsilon, in the sense that the epsilon is the expected value of the phi. So the shape of the phi depends on the Monte Carlo scheme that we are looking at. So different Monte Carlo schemes will generate different shapes of the phi, but the expectation of the phi is supposed to be epsilon, to be an unbiased estimator, epsilon. So the standard method to quantify the efficiency of the Monte Carlo scheme is the relative error, which is given as the square root of the sampling variance of the estimator normalized by the epsilon. Okay. So in case of the plain Monte Carlo scheme, the estimator is just the indicator variable, as I highlighted, right? So in case of the plain Monte Carlo, it is well known that the relative error explodes to infinity as we decrease the value of the epsilon. It's well known. And it becomes even more notorious for estimating the conditional expectation because, as we have seen before, this small epsilon is in the denominator. And what's known is that, approximately speaking, the relative error of this conditional expectation is going to be asymptotically the product of the two relative errors for the numerator and the denominator, and both the numerator and denominator include the indicator variable. So when epsilon goes down to 0, the relative error of the conditional expectation becomes even larger under the plain Monte Carlo scale. So our hope is to get a bounded relative error in the limit when the denominator epsilon vanishes. So this certainly motivates something called the variance reduction scheme across different Monte Carlo schemes. And one of the most well-known scheme is something called importance sampling, okay? Whose intuition is basically to shift the sampling process from a very difficult to sample distribution to a more manageable and easily collectible distribution based on the major change state. Of course, once you change the distribution, the estimated value is going to be biased. So we need to use the measure change theory to correct the distortion in some sense. Anyways, the important sampling basically aims to choose a good distribution for the variance reduction based on the measure change argument. But we have the caveat is that if we fail to choose a good distribution, the estimator is not going to be the variance reducing estimator any longer. In some cases, if we fail to choose the optimal tilting parameter, for instance, it's going to be a variance exploding estimator in many cases. So great care must be given in terms of the implementation of the important sample. Okay. So here's a bit of intuition behind our approach. Okay. We can say that our approach is a very special example of the important sampling scheme, but it's quite special in the following sense. Okay, we introduced two different probability measures. Here, P stands for the reference probability measure, the usual probability measure that's going to be used for the claim of the call. And our strategy is to construct a very special probability measure, say P star, which we call the conditional tail sampling measure, which is certainly distinct from P, such that under this new probability measure P star, the tail event that we are focusing on is going to be realized for sure. Okay, it's quite ambitious, but that's what we are actually aiming for. Okay, so definitely we need to correct the distortion because that event is going to be realized always, almost surely under P star. So we're going to draw the samples of the adjusted bias. Okay, how? Okay, what's going to be the adjusted estimator to get an unbiased estimator for the epsilon? Here's the intuition. Okay, basically the epsilon is expressed as the expectation of a whole bunch of indicator variable under P. So usually this indicator generates huge amount of the sampling variance if we naively implement a Monte Carlo scheme. But under P star, by changing the measure, if this condition is satisfied, then this indicator variable becomes just one, is constant. Okay? But this P star is not going to be a zero variance measure because the thing here, which we usually call as the Radon-Nikodym derivative, which governs the measure change theorem, generates some variance. Our hope is to make this Radon-Nikodym derivative relatively less variable. Okay, so the thing is that in this expectation, if we take a look at this expectation, this expression, this phi Radon-Nikodym derivative is going to be the unbiased estimator under this P star to estimate this epsilon. Okay. So the first question to be addressed is, can we actually find such a pair of P star and phi? Our answer is always yes, as long as this epsilon is not completely zero. Okay? As long as even when the epsilon is small, but as long as the epsilon is strictly positive, we can always find such a probability measure P star and the relative unbiased estimator phi. More important but more challenging question is, can we achieve the bounded relative error under this P star as we shrink the value of the epsilon? The answer is not always, but I'm going to show you that we can achieve this bounded relative error conditions in many cases. If not, it's still powerful. Okay, so I'm going to talk about the details in a few minutes more. But anyways, this is basically our approach. The summary of our main contribution in this study, we propose something called the conditional tail sampling scheme to develop a novel and easy to simulate and fast Monte Carlo estimator of the rare event probabilities. And one of the beauties is that it can be applied to almost every model specifications as long as you can simulate the model. For example, if you can apply the play Monte Carlo on the given model, then our methodology can be also applied. Okay. And as I highlighted, our simulation recipe and algorithm guarantees that none of the simulated paths will be wasted. Okay. So it basically endures, each of the simulated path basically hits the rare event with probably one. So this is primary source that facilitates a reduction in the sampling error. Okay. Moreover, in terms of its implementation, we believe that our approach has some, attractive features for simulation. Okay. For one thing, our method does not require any of the computation of the optimal or the optimal tuning parameters. We don't have to find any optimal parameters in the middle of the simulation process. Also, we don't need to perform any of the numerical inversions or we don't have to calculate the distribution of the first hitting time or anything. They usually appear in classical importance sampling algorithms. Moreover, our method can be easily extended to estimate the conditional expectations of the rare events based on the base formula. Okay. So what's happening is that we can simply replace this indicator variable to some unbiased estimator under P star. Okay, that's going to be the only thing we have to do for estimating the probability that we estimate. And for the estimation of the numerator, we need to go through one more step, which is the transformation of x to something else, x star. But we will show that this transformation is going to be also straightforward in some sense. And I'll show you the details.
So, sorry, I'm a little bit, you have products in the numerator. I'm thinking about independence issues.
Right.
Why are you allowed to plug in like that?
So basically, this x is going to be our, interest, right? Some important random quantity that may generate some huge problem under the rare event circumstances, right? So by taking advantage of the base formula, we can express this conditional expectation as the ratio of the two unconditional expectations. Right. And on the numerator, what happens is, what we need is the unconditional distribution of x multiplied by the indicator, but this indicator will generate a huge amount of the direct sampling error under the plane of the color. So we will change the problem measure by replacing this indicator to something phi that I'm going to explain later. But under P star, this x must be somehow transformed into something new. But what I'm going to highlight is that this x hat is going to be straightforward. I mean, the estimation of the calculation of x hat on the P star is also straightforward in some sense. I'm going to talk about the details.
So you're going to replace one product with another.
Exactly.
One measure with another. These things are going to be equal. And is this data driven in some way, or is this all theory?
It depends on our model specification. But the point is that as long as the model can be simulated in some sense, our methodology can be also applied by these. Okay, so I'll show you the application of our algorithm based on some numerical illustrations to illustrate the superior performance of our proposed conditional chaos sampling scheme over the plane of the color. So here's my agenda for today's presentation. The first part, I'm going to focus on the estimation of the tail probability epsilon, okay? And then we're going to move on to the next part, which is the conditional expectation on the tail. So in this case, the first part, estimation of the tail probability, is going to be kind of the prerequisite, because once we achieve the estimation of this epsilon, then we can also estimate this conditional expectation by estimating the numerator part. So that's going to be my the agenda for my presentation. And finally, I'm going to show you some practical applications to the finance and insurance risk management, risk assessment. Any further questions so far? So here's the detail about the tail probability estimation. Okay, so we need to pave some way. Okay, here is our strategy. Our strategy is to fix a measurable space first. Okay, on a fixed measurable space, we are going to construct two different probability measures, P and P star, where the P stands for the reference measure for the plane of the color, and the P star is kind of today's featured item as the conditional chaos sampling measure for our CTS scheme. Okay. So what happens is that we first introduce a sequence of the order stopping times, which will represent each of the event or times on the measurable space. And two different problem measures, P and P star, will assign different probability distribution on these stopping times. Okay. But anyways, once we introduce the stopping times, then we define the counting process like this. This is another way to define the counting process in the sense that we simply collect the number of events up until the given time small t. Okay. Then we introduce something called theta L, which represents the inter-arrival time between two consecutive event arrival times. The key is that the P and P star, two different probability measures, will assign different probability distributions on this theta L. That's the point. Next, we construct a sequence of non-negative process, say HL, in the sense that each HL is going to be activated between the event arrival times. And the initial value of each HL is going to be based on another sequence of the variables, say ZL, in the sense that the first H0 is going to be just the first Z. And then up until the next arrival time, it moves forward based on its transition law. And then the initial value of the next HL is going to be constructed based on this ZL and the last value of the previous HL. Okay, and it goes on. Okay, so we construct the process lambda as simply connection of those HLs. So the question is, why do we construct this process, and what are those processes actually are? Okay, it depends on the way how we assign the probability distribution and the probability behavior of those processes. For example, we'll take this HL as the conditional inter-arrival intensity of the counting process based on the time chain theorem of Meyer. Okay? We basically introduce an IID sequence of the standard exponential random variable. And then we assign the probability distribution of theta L by simply redefining this HL as the random heating time based on the integral of this HL, which is the standard exponential random variable. Then what happens is that this HL becomes an inter-arrival intensity of n is connected value lambda is going to be the intensity of the event counting process n, in the sense that the lambda now becomes a conditional mean arrival rate under P. This is how we construct the plain Monte Carlo framework. But the lambda and HLs will be totally different things under P star, and this is going to be the highlight of today's presentation. Okay? So this is the way how we construct the conditional tail sampling measure P star, specific tail events, step by step conceptually. The first step is to take some arbitrary, strictly positive constant, say gamma. Okay, for any given positive gamma, we first construct the well-defined probability measure, say P gamma, as the probability measure defined on the given measurable space, under which the counting process n adopts the gamma as its intensity up until the k event arrival point. In the sense that up until tau k, under P gamma measure, this n will be just a time homogeneous Gaussian process with the rate of gamma. Okay, and after tau k, the intensity of n becomes lambda ts again. Okay, so we get back to normal kind of. And based on this P gamma thing, we construct the second step of the measure, like P star gamma, as the P gamma probability conditional on this event. Okay, this is the key step. So this P gamma star, okay, is not an equivalent measure to P. It's just absolute continuous probability measure with respect to P. But as long as gamma is positive, and as long as this conditional event has non-zero probability mass under P, this conditional probability P star gamma is going to be still a well-defined probability measure. Okay. The next, we take the limit by approaching to zero, by taking the gamma to close to zero to get this limiting measure. This is our conditional tail sampling measure that we're going to use for our simulation of it. Okay. So be careful, we are not simply taking zero as a value of gamma. We are approaching to zero to guarantee that this gamma is always strictly positive. Then this limiting measure exists, and it is going to be a well-defined under the Baeho theorem for convergence of the measures. Okay, so here are some key items that we need to focus on as the primary properties of the P star. First of all, as I mentioned, this P star is not an equivalent measure, but absolute continuous measure with respect to the ordinary measure P by concentrating all of the probability mass on this tail event, in the sense that we certainly satisfy the requirement that that rare event will almost surely occur under this P star. More importantly, under P star measure, the sequence of the event arrival times, tau 1 to tau k, forms the uniform order statistic. This is one of the key properties for simulation. So usually for most of the Monte Carlo simulation methods, with respect to the event arrival timing model, the bottleneck is to generate the realization of this event arrival times. That usually takes most of the times for the simulation. But in our case, once we take the P star as our simulation measure, the distribution of each tau will be just uniform distribution. And I believe that generating the uniform random variable is going to be one of the cheapest one in terms of the computational perspective. So it's going to be quite straightforward to implement this simulation method. Okay. So here's our main theorem. So we first introduce a sequence of the IID uniform order statistics between time 0 and capital T. So we call them as ULs from 1 to K. Then we redefine the space in theta L as the difference between two consecutive uniform order statistics by simply taking the tau L as UL. So in this sense, under P star, simply because we are drawing the K different IID uniform random variables, observing K events within the horizon T is going to be guaranteed. Okay. Then the theorem says that this guy, okay, which I will explain more carefully, the phi KT here is going to be the unbiased estimator of this epsilon under P star. Okay. And what is this phi KT? Okay, this is actually the radionuclide derivative, which governs the major change from P to P star, but it's going to be expressed in this way. Okay, first, this constant Tk over K factorial. As long as T and K are given, this term is just a constant term. So we can simply take it out from the expectation operator. So it's pretty much straightforward to compute. And the rest is the product of the whole bunch of eta L's. If you have some, prior exposure of the point process estimation, it's nothing more than the evaluation of the likelihood function of some point process model by taking these ULs as the real observed event arrival points. So as long as the intensity model specification allows us to evaluate the likelihood given some event arrival times, this term can be also calculated. And we simply take this sampling average to take this expectation. That's going to be the unbiased estimator of this epsilon. Okay. So in terms of the Monte Carlo simulation, again, what I mean by this expectation is just taking sample average. So from now on, I'm going to use expectation and expectation star interchangeably because it means just taking sample average. So here is the summary of the simulation recipe. Okay. So first step to do is to generate a whole bunch of the uniform random variables. Okay. So P and K are given. So we first draw an ordered sample of the sequence of ULs from U1 to UK, and all of them are uniformly distributed. Okay, so we generate a uniform order statistics, and then based on each of the ULs, okay, we generate the sample trajectory of the HL processes. Okay, given the initial value of that until the next event time. As long as the transition law of the HL process is given, we can simulate the next time, and then we evaluate this natural thing. Okay, and it's like evaluation of likelihood as a likelihood function. Okay, so we generate a whole bunch of different phi KTs and return the sample mean of those estimators, and that's going to be the estimated tail probability. Okay, the point is that by design, this phi k will never take the value of 0. And also by design, its expectation is going to be just small values. So we hope, our hope is that it will generate small amount of the sampling variances. Okay. And one more thing, okay, if we restrict that no more events will occur after UK to the capital T, then we can also evaluate this point probability. Okay, so previously, this estimator is the probability with this inequality, but it's easy and straightforward to extend the concept of this point of conditional pair sampling to the conditional point sampling, in the sense that we can get the unbiased estimator for this probability as well. So if we can also generate the full distribution of the NT across different cases based on this method, as long as the probability is small. And one more extension may be applied to the doubly stochastic blossom process, in the sense that if the point process is modeled as a doubly stochastic, in the sense that no arrival time may affect the dynamics of the intensity, then we can apply the same conditional sampling scheme on the time change axis, not the ordinal time axis. Then it will usually generate a closed form solution or the semi-closed form solution for the scale probability. So it will greatly reduce the amount of the computation effort that we need to put for estimation of this type of probability. But even if the process is not doubly stochastic, for example, self-excited process, this methodology is not going to be available, but tail sampling scheme can be still available to be applied on the original time axis. So we can still apply that, and I'm going to explain some of the important features and then show you some numerical results. Okay. So this is a symptotic analysis for boundary relative error theorem. Okay. So here we consider the symptotics when this T over K converges to 0. Okay, this is one of the regions that absolutely converges down to 0 because we're going to shrink the investigation horizon, or we are going to increase the number of events that we need to observe within the time horizon, or both. Okay, so we take the X as the rare event parameter when X goes to infinity, and we suppose that this T over K goes down to 0. Then the theorem says that the conditional sampling estimator will achieve this symptotic boundary relative error if those two following conditions are satisfied. Okay. The second condition is more straightforward to understand. This means that the intensity value never gets 0 value up until the time capital T. So as long as we guarantee that the intensity process or the interval intensity process never achieves 0 value, then the second condition will be satisfied. And the first condition is more difficult to generalize. This is very general form, but the specific condition for the first statement, the first condition is going to be model dependent. It depends on the model specification. But roughly speaking, the larger the K, the smaller P, the level of the lower the level of the intensity, and especially the smaller the variation of the intensity process, then we can achieve the first condition. Okay. So this is the boundary relative error theorem, and for the rest of time, I'm going to show you the example. Okay, for the first problem. So I think it's going to be more conceptually easier to understand the focus of our methodology. Okay, the first example will show you the way how we can estimate the tail probability regarding the epidemiology network. Okay, or a risk analysis model, how disease can be transmitted with network population. So the structure of the network is very important to study the dynamics of the disease transmission. And one of the starlight effects easily observed in the human-made system is that it usually contains only few nodes called hubs or some influencers, okay, with unusually high degree as compared to the other nodes. So we take the what we call BA model, in the sense of the Barabasi-Albert model, to address these realistic aspects of the network structure. As you can see, this network structure is going to be used for our simulation study. We can observe that some of the observable hubs or influencers will take most of the subscribers, right? So it reflects something called the scale-free power law of degree distribution, okay, which is typically shown in the human-made network systems.
Can you talk more about the Barabasi-Albert model? It's fascinating.
So as you can see, the issue addresses something called the preferential catching feature, which means that as the network grows, we can definitely observe only a few nodes that will attract most of the relationship. So that only a few nodes will show unusually high degree, as you can see, right? So it reflects the scale-free power law of the degree distribution. That's one of the important aspects that highlights that will be addressed by this Barabasi model, I believe.
It's like a rich get richer model.
Yeah, in the YouTube world, only a few of the influencers will take most of the subscribers, right?
Like in real life.
In our real life. So we try to address this kind of stylized effect. So here is our bottom-up formulation of the self-exciting intensity specification. So here, small n is the size of the entire population, and we assume that each agent has the infection indicator process, in the sense that 0 means that agent has not been infected, and 1 means that the agent is infected. And the intensity is going to be specified as a linear combination of two processes. Here, x0 is a systematic risk factor as a common source of the indirect transmission, and what's more important in our modeling strategy is xi as a set of the idiosyncratic factors as the drivers of the direct contagion. And as you may expect, this idiosyncratic factor process includes the self-exciting terms. Here, delta ij indicates that if, for example, the agent J gets infected, then the likelihood of the agent I's infection increases by the amount of the delta ij, and we address the property of the Barabasi-Albert model by assigning this delta ij's. Okay. So the aggregate intensity is just sum of the individual infection counting process intensities, and here we take this n as the key parameter. Okay, so here we take the n as the rarity parameter for estimating this tail probability, and we design that both t and k are also function of n's. So in the sense that tn is an inverse function of n, and kn is just 10% of the entire population. So what I mean is that as we increase the size of the population in the network, as n grows, what happens is that we increase the size of the network and shrink the investigation horizon while keeping the threshold at the 10% of the population. So we try to estimate the tail probability by varying the value of n from 100 to 500. And each simulation estimation, we allow the fixed amount of the simulation budget by allowing 60 seconds of the CPU time for each estimation. So left panel shows the estimated probability, tail probability based on the play Monte Carlo in black, and our proposed method of conditional tail sampling scheme in red. This left panel shows the estimated probability in the form of the 99% of the confidence interval. So the first observation is that both the play Monte Carlo and the tail sampling scheme will generate unbiased estimator of this tail probability. But as we increase the rarity parameter n from 100 to 500, as you can see, the width of the confidence interval for the play Monte Carlo gets wider and wider, which means it becomes certainly inefficient. But the red line, it looks like just a line, but actually it is confidence interval. Okay? So it shows much superior efficiency, which can be also highlighted on the right panel, okay, which shows the relative error of the simulation method schemes between the play Monte Carlo and the conditional tail sampling. This is a log scale. So as we increase the n, the target probability becomes extremely small. But even if we increase the n, the relative error of the tail sampling scheme is going to be relatively stable, whereas the play Monte Carlo's relative error explodes. Okay? But I'm not highlighting that our method is always good, because, for example, when n is 100, the probability is over 70 or 80%. It's not a rare event any longer, right? In such a case, play Monte Carlo may be better. The point is that as we jump into the deeper tail, okay, by increase the value of n, the conditional tail sampling scheme will be much more efficient. It's our first observation. Then we move on to maybe more practically important question to estimate the conditional expectations on the tail. Okay? Because, for example, who would care the probability even less than 10 to the negative 10? My answer is it is still relevant in terms of the conditional expectations. Okay? Even if the probability is going to be small, what would be the expected consequence of if that happens? Okay. So this kind of the estimation of the conditional expectation on tail events can certainly facilitate a better understanding of how some important random quantity behaves in such rare events scenarios. Again, the key is to apply the base formula, and we have already addressed the problem of the denominator estimation, so we're going to focus on the numerator part. Okay. Again, the point is that we don't need any knowledge of the conditional law of X on the tail events. Okay. So usually to address the distribution of behavior of this quantity X, we extend the concept of the point process to say marked point process by considering another sequence of the random quantities, like the random losses, in the sense that the loss process L at some time small p is going to be defined as the sum of these marks, okay, from 1 to n t. Okay, so it represents the sum of the random losses at each event around the time. So the way how we address the distribution behavior of this pi L, the marks, we can also address the distributional behavior of the random quantity, usually the loss in given event scenarios. Okay. So here is our target to estimate. We're going to estimate the expectation of some loss over a longer horizon, say T2, conditional on the tail event over a shorter horizon T1. So the question is something like this: what's going to be the total loss over the next 1 year if something really bad happens over the first 1 month or something? Okay, this is gonna be a very important problem in many from many aspects. Okay, so we can extend the tail sampling scheme specific to this problem in the following sense. So we have 2 time horizons, T1 and T2, okay? And between time 0 and time T1, we're gonna be the tail sampling regime. Okay? We are kind of dreaming a disastrous nightmare until time T1 by forcing that we have to observe K events within time T1, okay? Then we generate the simulated trajectory of the event horizon intensity. Actually, it's not an intensity process under P star, but we take it as a kind of fake intensity because we are dreaming of nightmare, right? And then at the end of the last event time, then we wake up in the morning and we get back to normal, okay? So it's kind of connection between the nightmare and the normal life. But the thing is that the initial state of our normal region in the morning is going to be the last state of the nightmare. This is our conditional tail sampling scheme in in the context of the conditional expectation estimation. So here is the theorem of the extended conditional tail sampling. What we need is the expectation of this thing. This is going to be actually the numerator of the base formula to estimate the conditional expectation, right? And the theorem says that the unbiased estimator of this expectation on the left-hand side is going to be the right-hand side. Okay, so the indicator is going to be replaced by the phi kt, and this phi kt is just exactly the same phi k for estimating tail probability. Okay, so we have the same strategy, and since we on the P star we have simulated the event horizon times based on the uniform order statistics, and based on that observation, we can easily simulate the loss process as well, because usually the loss process is a function of the event arrival times, and on the P star, the event arrival times are distributed uniformly. That's it.
Could you remind me what 5KT1 does?
Okay, 5KT1. I think I should go back. Is this thing. Okay, it's this thing. And what is this one? This is an unbiased estimator to estimate this tail probability. And this is also a rather liquid derivative which governs the measure change from the original P measure to the P star measure for our simulation. Okay, so everything is connected. Thank you very much for asking the question. Right, and moreover, the next theorem says that the relative error to measure the efficiency of the estimation of conditional expectation is bounded as the product of the 2 asymptotic relative errors. This one is the relative error, asymptotic relative error of the denominator, which is the unbiased estimator of the tail probability. And this one is the relative error for the numerator. Okay, so if the unbiased estimator of numerator and the denominator are also bounded, then the relative error for the conditional expectation is also bounded. This condition is straightforward in the sense that in the variable regime, usually the loss flows. So in most cases, the condition is satisfies. So we can still apply the bounded relative error theorem in this context. Right? Second example, okay. This example is related to the systemic risk, which usually arises in the finance, right? So we're going to examine the potential consequences that a system or a market may face in extreme tail scenarios in pretty short horizon. Okay, so we're going to focus on two things: the probability, tail probability, and the condition expectation. Here we take X as a rare event parameter. So what we design is like X, as X goes to infinity, the investigation horizon Tx shrinks, and also the number of threshold Kx goes to infinity. Okay, so we are gonna, this is how we design the rare event regime. So the condition expectation, well, just one second. Condition expectation says that if we shrink the investigative horizon, if something really bad happens on the beginning of short horizon, then what's going to be the expectation of the number of events over the entire time period capital?
That's right. So what would be the interpretation? Like, could you like intuitively as X goes to infinity means that the extreme event, the size of the extreme event goes to infinity?
Yes, right. So as X goes to infinity, what we require is that the probability, this probability goes down to zero. So it becomes even more rare event.
So
the condition on this extremely rare event, what's going to be the condition expectation of this number of events in total over the entire horizon, right? Thank you. I believe this will give us a very important and crucial understanding of the distribution behavior of this thing, conditional on the rare event that we are concerned
You're
about.
trying to model as the size of the extreme event gets larger, the time frame of that event is actually shorter.
In this example, yes, and it makes some practical sense, we believe, because in user case, if we enlarge the scope of the investigation, if we think about the constraint on our risk assessment capacity in practice, usually naturally we need to shrink the investigation horizon. And also, if we shrink the investigation horizon, this probability becomes even smaller. So this is also consistent with the tail event analysis. So this is the result for the estimation of the probability. This is the first step, right? So in this example, we take the Tx as a T over X. So as X becomes larger, Tx becomes shorter, right? And also we simply set the Kx as 5 times X. So for example, the capital T is 5 years. So if X is 5, that means the probability of observing more than 25 events over the next 1 year. And something like that. So here again, the left panel shows 99% confidence interval for the estimated probability between the plain Monte Carlo in black and the tail sampling in red, which, okay, both of them generates unbiased estimator of this tail probability, but the thing is that the plain Monte Carlo fails to generate any single occurrence after this point when X is 5 or larger. Okay? That means the relative error cannot be calculated. But as you can see, our tail sampling scheme will successfully generate all of the probabilities quite accurately, even if the probability becomes really small. Okay, and except for the case when X is 2, our tail sampling scheme is a way more efficient than the tail sampling scheme to estimate the probability, tail probability. Next step is to compute the condition expectation. Okay, this is the condition expectation of the number of events over the next 5 years, condition on this tail event, right? So as expected, the condition expectation will increase, but how it increases, if the distribution behavior of this conditional thing is going to be crucial. It's usually not very well known simply because by definition it's rare event. It's hard to be observable in real life. Okay? And also, just like the previous one, the plain Monte Carlo scheme fails to generate any of the estimated value, its condition expectation after the point of X equals 5. And pretty similar results can be observed for the relative errors.
So what you're trying to say is that you can actually estimate the slope of the trajectory of the future consequences. Is that?
This is conditional expectation, right, on average, and conditional on the event that we are concerned about. This is very important, crucial point, right, to investigate. And it's not just for the financial system and risk analysis. It can be also applied to, for example, the healthcare, policy-oriented investigation, something like that. It is quite relevant to a wide range of the problems. So for the rest of the times, I have 20 minutes or so, right? I'm going to show you a couple of more applications, real-world applications that can be highlighting the merit of our methodology in finance. The first example is about the default of a security pricing over very short pricing. Right? For example, suppose that you need to estimate the fair amount of the credit spread for some risky bond whose maturity is very short. Okay. So why is it practically relevant for this? For considering the small time capital T? Okay. Two examples, maybe at least. For example, the central bank adjusts the DIF rate, which stands for the daily interest facility, to account for the overnight credit spread. So in this example, the investigated horizon is overnight, right, within 1 day or something. And especially if we think about the growing prevalence of the blockchain technology, which certainly enables the immediate settlement of the transactions in the real-life interbank money market, what happens is that we need an ultra-short tenor interest rate curve that can be estimated at the intraday level, at an hour or even minute level. So within this kind of extremely short time horizon, what should be the fair amount of the credit spread that you need to charge or you need to pay? Okay. So by definition, for example, if the time horizon is just 1 hour or even 5 minutes or something, under the plain Monte Carlo simulation method, it's going to be almost impossible to generate any single observation in the scenarios. But definitely the credit spread cannot be zero, right? So to highlight the merit of the Monte Carlo simulation, we try to make the model quite complicated at a reasonable level. For example, we impose that the default intensity process is a combination of the short rate process and something else, a state process. We believe that this makes some sense because if the interest rate goes up, in general, the default intensity goes up as well. And also we impose that the loss process, which is a function of the recovery process, is a function of the intensity value at the time of default. So if the intensity value increases, the amount of the loss at the given default will increase as well. So in this setup, as far as I know, there doesn't exist any of the closing solution for the credit spread.
I have a question.
Sure.
Short rates, the short rate is a default free rate here?
Yes, default free rate, exactly.
This is like not really a continuous process. This is a very jumpy thing that the government comes in and says, okay, today it's going to be going up 1%.
Exactly. We also have that model result as well, but this is just an example.
This is not a realistic example. This is a
in that case, right?
Yeah.
So
okay.
We just try to make the short rate process as simple, but we try to make the default intensity process and the recovery process more complicated. But actually, as you said, the jump behavior is very important source of the uncertainty in terms of the short rate process risk, right? So we can definitely.
Okay, this just doesn't look like what's in my head when I think about short rates.
So we also have the model based on your suggestion, but not in this slide.
Okay. Oh, that's okay.
Right. Anyways, okay. So in this setup, this is just an example. This is a summary of some calculation to get the credit spread. Okay, credit spread can be expressed as some nonlinear function of this expectation. This is key. Okay, this expectation is some mark x, which is defined like this, as a function of the default event time tau. Okay, the tau matters here because of two reasons at least. One, based on our model specification, the recovery process is a function of tau, right? And also we need to compute the present value of the recovery value. So it's also a function of tau, right? So it's going to be a function of tau. This is important. And also we need the indicator variable. So if we change the measure from P to P star, in our case, under our conditional tail sampling scheme, this indicator variable will be replaced by this phi thing, okay? And this tau is going to be replaced by this uniform random variable between time zero and capital T. So even if capital T becomes smaller and smaller, this uniform random variable will be defined based on time interval between time zero and capital T. So this is going to be always simulatable, right? So we can always calculate this expectation. So this is the result. So here the left panel shows the estimated 99% confidence interval of the credit spread in basis point. And my x-axis on the left panel is the time to maturity in years. So for example, this means that the time horizon is 1 year, 1 over 10, 1 over 100, and so forth. So our focus is this area. So for example, if we focus on the daily horizon, 1 over 252, it's going to be somewhere around here, right? And I'm going to be, I think that this is going to be the case when we consider the median level of the horizon. Okay. So as expected, the plain Monte Carlo certainly fails to generate the credit spread at the median level. Okay. And even at the daily level, the confidence interval is so wide. For example, when the time to maturity is 10 to the negative 3, the lower bound of the 99% confidence interval is negative, which doesn't make sense at all, right? But if you take advantage of our proposed tail sampling scheme, it will generate unbiased estimator. What I mean by this blue line is the true value of the short horizon limit of the credit spread. In this case, okay, since we adopted quite simple risk-free rate model, we can take advantage of this credit spread, the limit of the credit spread, which is usually called as the credit triangle formula by multiplying the initial value of the intensity times the expected value of the loss at the beginning. So it says that our estimation result will successfully converge to the limit. Okay. But in practice, even if this limit is known, what matters is that, for example, within the median level, what should be the difference between the actual credit spread versus this limit? And if the difference is wider than the confidence interval generated by our tail sampling scheme, and the difference is going to be still median, right? On the right-hand side, we measure the relative error, the burden of relative error, across different simulation budget CPU time, okay? By fixing the time to maturity at the 1 day level. So as you can see, this is the relative error expressed in the log scale. We can say that approximately, the tail sampling scheme is approximately 1,000 times more efficient than the current Monte Carlo within the same amount of budget. So to achieve this 1,000 times of the efficiency in the spirit of the Monte Carlo simulation, we need to generate 1 million times more of the simulation sampling, right? So it's quite impressive, we believe. The next example is more related to the insurance risk analysis. We try to estimate the conditional expectation of the maximum drawdown, okay, which usually measures the largest reserve draw from its peak to trough, which is some time horizon. Okay. So we take a quite standard reserve process model. This reserve process model is quite simple in the sense that we have an initial value, and we just assume that this constant alpha, which is positive growth rate, okay? And this L is the mark project for the process. Okay?
L is the
the total amount of the loss coverage that is, the insurance company is responsible for up to time small p. Okay, so between time 0 and small p, we observe the arrival of the claims, right, from the customers. And at each claim, there should be the amount of the coverage. So LP is just cumulative sum of that. Okay. So we define the maximum drawdown, okay, which is the maximum of the drawdown. And drawdown is expressed as the maximum of the reserve minus the current reserve. So even if the reserve process is quite simple. The maximum drawdown is a very complicated function of the event arrival times. Okay, yes. So we still need the simulation method. So our estimation is our goal is the estimation of this expectation of the maximum drawdown conditional on some variance. Okay. So here for simplicity, we set this t is the same as this t, but definitely we can make them different. So in this example, we adopt the Markov reduced switch model for the dynamics of the stochastic claim intensity process. So it's piecewise constant, but it will alternate the regions between the normal region and the crisis region. And we assume that this is just based on the Markov reduced switch model, in the sense that the intensity process is independent of the counting process. So this is in this case the point process, the counting process satisfies the doubly stochastic property. So here's the result, okay, for the estimation of the tail probabilities. So we change the value of k from 5 to 40 in this example, okay? And capital T is 1 year. Okay, so the result is that again the conditional tail sampling scheme that we propose shows a much more efficient variance reduction performance under this stochastic region changing intensity dynamics. Because if you take a look at the relative error, the trend, even if we increase the t, even if we increase the k, the number of claims within the time horizon, the relative error for the tail sampling scheme is relatively stable. Okay. And more important one is the second step, the conditional expectation of this maximum drawdown. Okay. To compute this one, we need to rely on the Monte Carlo simulation. But again, in terms of the performance of plain Monte Carlo scheme, we certainly fail to get any of the estimated value for this expectation when the threshold becomes 40 or even larger. But based on the tail sampling scheme, we have a firm understanding of the behavior of this maximum drawdown, which is the random probability that we are interested in, conditional on some tail event that we are concerned about. And in this case, what is interesting is that the relative error based on the tail sampling scheme actually vanishes as time goes. As we increase the value of k. This is just a numerical result, but this also highlights the superior performance of our methodology over the plain. So I think this is the conclusion. Okay. This study basically develops something new and easy to simulate and quite fast and efficient Monte Carlo estimator of the variant probabilities and the conditional expectations, which we call as conditional tail sampling. We call it as conditional tail sampling because it's motivated based on the conditional probability measure that you get. And again, as long as the model is simulatable, okay, by applying the Monte Carlo, we can certainly apply the conditional tail sampling scheme. The computation is just two things: generation of a bunch of new linear variable, which is very cheap to generate, and the evaluation of the likelihood. So if you think about the classical important sampling schemes, is the Radon-Nikodym derivative must be calculated, and it is usually expressed as a likelihood ratio. So the likelihood ratio in the numerator is our likelihood ratio. And in the classical important sample, we need to compute something more in the denominator. But in our case, we simply take the limiting measure. So the complicated thing in the denominator will vanish, will collapse to just 1. And what is remaining is just a ratio between t to the power k over k factor, which is constant. So I think the evaluation of the likelihood function is unavoidable in the context of the sampling, but our method kind of minimizes the amount of the computational work. So the performance of the variance reduction is quite impressive from our perspective, and it certainly facilitates a substantial reduction in the sampling error. And based on our numerical examples, on the wide spectrum of applications, we find that this conditional tail sampling scheme is quite impressive. So we believe that this methodology has great potential for the application in a wide range of the real world problems like healthcare systems, healthcare problems, and the finance problems, and any other policy oriented problems, as long as the variant of counting problem is concerned. So this is all I prepared. Thank you very much for listening.
I have a question. Have you, I love that you brought up drawdown, which is the risk that all
Right.
investors care about and none of them actually work with, because nobody can forecast it. And there's a lot of data available on this empirical data. Have you tried?
You mean the estimation? Right?
Yeah, have you tried using in that area? I think there would be a lot of,
My answer is not yet.
yeah.
But again, even if our goal is to estimate this conditional expectation of the maximum drawdown, what we need is unconditional distribution of the maximum drawdown. So you can actually fit the model based on the normal situation scenarios, and then you can still compute this conditional expectation of the maximum drawdown. So the estimation problem doesn't require us to observe the rare events actually in this case. So yes, you're right. One of the reasons why I chose this example is because I think this is a very relevant problem.
It's a very relevant
Yes,
problem.
exactly. And it's not easy for me to search for a good reference which deals with this kind of problem so far.
I have some.
Oh,
I
so,
would send those
I
right
mean,
over.
conditional to some rare events. That's what I mean. Anyways, you're right. I think this kind of problem is very relevant and promising, and I think that the problem is going to be, that must be investigated by more researchers.
Great.
So I know that you have wrote some of the papers related to maximum drawdown. I came across some of your papers, and if you can recommend some of the more references,
Sure.
you'd be very appreciated.
There are some, and I think there is a lot of interest, but
Sure.
no, nobody really knows what to do about this.
Exactly.
But everybody would like to
You know, even in this simple, model of the reserve process, it's quite complicated random variable in terms of the specification of the maximum drawdown. The distribution of behavior of this guy is really known. Not to mention under the element scenarios.
Yeah, may I ask
Sure.
another question?
Yes, please.
So following up to that question, so you're saying up to time t, let's say different lenders have different resolvable characteristic, they have up to time t.
Mhm.
And then we're trying to forecast what would be the expected, a conditional expectation of the extreme values.
Right.
So could we also do something like, so each lenders have different characteristics up to time t, therefore they have different beliefs about the future. So that, is it possible to actually map all these different characteristics that are observable up to time large t, and then calculate so that we have different values for each lender?
I think that's a very valid question. I think the point can be fully addressed by the model specification and the parameter values that you impose, right? So depending on the model specification, along with the values given to those parameters, I think definitely the point that you raised can be addressed by the model, and given the model, we can apply this kind of. So applying this simulation method is based on the assumption that we have already calibrated the model, we have already specified the model. But I think that our methodology can be also applied to some inference problem as well. Okay, so that's a good point. Thank you very much. Any further questions?
Any more questions? Okay, well, thank you so much, Baeho. That was really great. Or do you have paper slides recording we can post on CDAR?
I've already shared the slides, but we are still working on the draft. So
Yeah.
we complete the write-up process.
Okay.
Definitely we will share.
But we can get the slides and we can post the recording.
Thank
Okay,
you.
so you should look for that on the CDAR website, AQ. Next week, at this time, we will be virtual only. My old friend and collaborator Samim Gamami, who's currently at the FCC, is gonna talk about skin in the game, risk analysis of central counterparties. So hope to see many of you over Zoom this time next week, not in this room.